So here we have the 2019 acid-base question. Again, it was a question and it came up in question 7. So the first, let's change that color. The first question that they ask us is to use equations to show that when dissolved in water, first of all, HCl acts as a Bronsted-Lowry acid. And second, that NH3, which is our ammonia, behaves like a Bronsted-Lowry base. Okay, so we know that a Bronsted-Lowry acid is a proton donor. So this HCl, if it behaves like a proton donor, it's going to give that proton to water. And we're going to be left with Cl- and H3O+, the hydronium ion. Now NH3, if that behaves like a Bronsted-Lowry base, that is a proton acceptor. So it's going to accept a proton from water, and it is going to form the ammonium ion, and we're going to have the hydroxide ion left over from the water. Now it's not asked here, but just a little quick recap. If we have a look at water here, in this equation it's behaving like a base and accepting a proton, and in this equation it's accepting, or it's behaving like an acid because it's giving away, or it's donating a proton. And the word for a substance that can behave like an acid or a base is amphoteric. So I have seen that asked a few times, so just make sure that you're aware of that definition. Okay, part 3. Explain why hydrochloric acid has a weak conjugate base. Now we know that hydrochloric acid is a strong acid, and we have a general rule that a strong acid produces a weak conjugate base. Now why is that? Well, if we have a look up here at this equilibrium system, if it's a strong acid, that means that the equilibrium lies on the right, because we know it almost fully dissociates, or our definition by Arrhenius is that it fully dissociates. So the equilibrium lies on the right, the forward reaction is favoured, and we get lots of our products produced. Forward reaction favoured. Now, if the forward reaction is favoured, the reverse reaction, which is where the chloride is behaving like a conjugate base and it is accepting a hydrogen in order to go back into the hydrogen or the HCl, because the forward reaction is favoured and the reverse reaction is not, it makes the chloride ion a poor proton acceptor. The next part is, why does NH3 have a strong conjugate acid? Well, NH3 we know is a weak base. And again, by our rule, a weak base has a strong conjugate acid, but why is that? So again, if we have a look at the equilibrium system up here, if it's a strong, or if it's a weak base, that means that equilibrium is going to lie on the left, which means that the reverse reaction is being favoured. Which means that our NH4 can quite easily donate that hydrogen to revert back into NH3. So the NH4 plus is a good proton donor because the equilibrium is lying on the left. So it's very likely that that NH4 plus is going to donate that H plus. Okay, part B. So part B gives us an equation for the self-ionization of water. And it asks us to write the self-ionization constant, or we would have called that the ionic product of water in class. So B part 1, Kw, we know is the product of the concentration of the hydrogen ions times the concentration of the OH minus ions. But if you notice in this equation up here, they give us the H3O plus. So I might just rewrite that as the H3O plus or the hydronium ion concentration times the hydroxide ion. Now, they ask us about this table of data. So you can see we've got temperature, and the temperature is increasing, and then we've got the ionic product of water, Kw. So they're asking us, is the data in the table consistent with the self-ionization of water being exothermic or endothermic? So if we have a look at the trend here, as the temperature increases, the Kw increases. Now, does that mean that the forward reaction is endothermic or exothermic? So, as temperature increases, we have seen that Kw increases. Now, if Kw is increasing, remember these H plus and OH minus ions are our products, which means that the forward reaction is being favored. So if the Kw increases, that means that we've got more products being formed, which means that the forward reaction is being favored. Now, if the temperature is increasing, the endothermic reaction is favored. Why? So if we increase the temperature, the endothermic, which is the heat absorbing reaction, is favored. So that means that we can make the conclusion that the forward reaction, which is the ionization of water, is endothermic. Okay. Part 3 then asks us to graph Kw versus temperature. So I have the graph here drawn. I'm not going to draw it out for you, but if you would like a video of me showing you how I drew it out, then by all means send me an email and I will send you a video of that. Now let me bring this question down here because it will save us scrolling the whole time. So here's our question and here's our graph. So we've done part 3. Here's part 3, plotting the graph. Now use your graph to predict the value of Kw at body temperature, which is 37 degrees. So let's change our pen color here so that we can see it. And they're asking us to find the Kw at 37 degrees using our graph. So let's find 37 degrees is there. So I'm going to follow this up to where it hits the graph, and then I'm going to bring that across. And obviously you guys can do this with a ruler when you're doing it on your own piece of paper. So that is going to give us an answer of 2.3 by 10 to the minus 14. So that's part 5. No, that's part 4. So we've got an answer of 2.3 by 10 to the minus 14. And if you check the marking scheme, they do accept a small range of answers just to take into account the fact that you might have graphed it slightly differently. So that is 2.3 by 10 to the minus 14 at 37 degrees. Now it's asking us to use this value to calculate the H3O plus, or the hydronium ion concentration of pure water at 37 degrees. So what we have said is that the Kw is equal to 2.3 by 10 to the minus 14. And we have said in the first part of this equation that the Kw is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. Okay. But we also know from our equation that the concentration of the hydronium ion is equal to the concentration of the hydroxide ion. So what I'm going to do is I'm going to actually sub this in for the hydroxide ion here, and I can say that 2.3 by 10 to the minus 14 is equal to actually the hydroxide, or the hydronium ion, multiplied by itself, which is basically it squared. So now I've got 2.3 by 10 to the minus 14 is equal to the concentration of the hydronium ion, 2b squared. There are a bit dodgy pluses there. So I'm going to square root that. And that will give me an answer of 1.51 by 10 to the minus 7 moles per litre, because remember those square brackets stand for moles per litre. Now, the final part is the pH of pure water is close to 6.77 at one of the temperatures in the table. Find by calculation this temperature. Okay, so we're going to have to calculate a kW and figure out which one it corresponds to on the table. So if we're told, let's just start this over here. So we're told that pH is equal to 6.77. So what we can do is use that to calculate the hydrogen ion concentration, because we know that pH is equal to minus log to the base 10 of the H3O plus ion concentration. So what I'm going to do is I'm going to use this to calculate the H3O plus concentration, and then I'm going to use that to calculate the kW, and then I'm going to find which answer that corresponds to in the table. So let's solve for the H3O plus concentration first. So I'm going to bring that minus across. So the concentration on my H3O plus is equal to 1.698 by 10 to the minus 7 moles per litre. Okay, so there's the concentration of my H3O plus. And I've already said that the Kw is equal to basically the H3O plus ion concentration to be squared, because I know that the concentration of the H3O plus is equal to the concentration of the OH minus ion. Dodgy brackets. Okay, so my Kw now is equal to 1.698 by 10 to the minus 7 2b squared, which is equal to 2.9 by 10 to the minus 14. Now let's go up to our table and see, can we find 2.9 by 10 to the minus 14? And actually, it's there in the table, 2.9 by 10 to the minus 14, and that occurs at a temperature of 40 degrees. So that means that my final answer there, where they asked me for the temperature, is 40 degrees. So that was an awful lot of work for the final part of that question. It was a little bit tricky because you had to draw a graph as well. So students were pretty much under time pressure for this question in particular. It's a lot of work to get there, but it's a very interesting question. So again, if you have any questions on that, or if you'd like me to draw that graph for you on a different video, just send me a message. That's the 2019 question on acid bases complete.